Safa Opera, hello.
What's up?
Happy Monday, people. What's going on? There, hello, everybody. I feel so loved right now. 3 people. Patrick, what's going on? That's okay. Probably good things. You guys like my new lighting setup? I feel angelic right now. Really doing interesting things with the textures and the contours of my hair. If anyone's a painter, now's the time to really get some interesting light. Just getting ready for math. Well, Patrick, I'll give you about 45 more seconds because math is about to commence. As always, math doesn't really wait for any man. At least math research. In a weird way, math research has been going on continuously for the last 3,000 years. No, 5,000 years, something like that. So the point is, if you're not ready yet, Patrick, then you've missed the bus. How was your weekend, everybody?
Very hectic.
Why hectic, Opera?
All I had was discrete math and linear algebra homeworks. Just math, and math.
Yeah, which in my mind is a great thing, but I understand that I'm not everybody. And yes, this homework was a bit longer, which is why I gave you guys a couple extra days. But the good news is, I think I sent an announcement that this got like the final push. Things are going like this is the climax of the class, and it's just following resolution from here. After we talk about induction, we're talking about set theory and functions and a bunch of other fun stuff, but it's not nearly going to be this high level, high energy everything. So sorry the homework was a bit long this week, but after the test, things are going to chill. We're going to have a super fun last 4 weeks of class. It's going to be almost more like there's a word for these guys, like a topics course after this. And I love that. I love topics. I love not going that deep into topics sometimes, because that's like YouTube videos. I could watch 12 hours of YouTube videos, barely going into the topic. So you kind of feel like you're learning, but you barely are, but you're getting a gist. And the gist is kind of the fun part. But anyway, Herman's here. So now we can get started. Waiting for you, Herman. I got you.
I have one more question. Are we having the review session today or not?
Good question. I wasn't going to last night because not enough people said they wanted to. Let's see if that changed overnight. Oh, we got 9 people. Sure. I'll make an announcement. I have a review session from 7 to 8. And come with questions. I don't have anything prepared, because this is supposed to be for because this is supposed to be filling in the gaps of what I've prepared. So I want you guys to come with the questions, so I don't just keep doing missing the same information.
So would you be able to answer questions from the written assignment which are not yet graded, just to understand the answer or the question pattern?
Yeah. Absolutely. So, but right now, so don't miss anything else, let's keep going today with another fantastic lecture of discrete math. Did not anticipate this glare. Let's see what happens. So I'll work on that. But anyway, is there like a weird line going up the screen?
It kind of looks cool. It's like, I don't know, there's a bunch of lines moving up the screen. I can still see the stuff clearly. There's just a bunch of lines.
Weird. You know what that is? That bums me out. Interesting. The light is an LED. So what that means, Oh, when I move, it kind of goes away. Interesting. So the light's an LED. So what that means is that it's kind of like turning off and turning on. Like if you had like a slow-mo camera, you'd see it's not on all the time. It's only on like a half the time or a third of the time or something like that. And the frame rate of the camera is like lining up with that in such a way, I think, it's doing that. Anyway, let's get going. Let me know if you have trouble seeing this, and then we'll figure something out. But anyway, today we're going to talk more about induction, of course. Yes, our great friend induction. And specifically, we're going to review weak induction and then do more strong induction examples. So for weak induction, let's kind of talk about maybe some edge cases here. Let's just go over what weak induction is again, so we all have it in our minds. So weak induction goes like this. I'll keep it purple. So weak induction. So to prove that for all in a set x and z such that x greater than or equal to a, p of n, with weak induction. Yeah. So to prove that this set x and z to the x greater than or equal to a, that's just all everything that's an integer bigger than or equal to a. So it's just all integers bigger than or equal to a. Greater than or equal to a. So to prove that for all integers greater than or equal to a, that p of n is true with weak induction, our proof goes like this. We say prove by weak induction on n. We normally name a variable. This is the variable that's going to go through things just so we kind of know what's going on. And then we start off with a base case. And that base case for weak induction is always going to be just the lowest number in your set. So since this is all integers greater than or equal to a, we're going to start with let n equal to a. And then here we want to prove that p of n, which is the same thing as p of a in this case, is true. So I'm going to start a little chain down here. I'm just going to note that based on the base case, p of a is true. And then we have an inductive step. Now here in the inductive step, we want to show that for all n greater than or equal to a, p of n implies p of n plus 1. Why do we want to show that? We want to show that because if for all n greater than or equal to a, p of n implies p of n plus 1, well, in particular, this works for n equals a, right? So I'll say note, okay, you guys can't see that. That bums me out. Okay, I can fix this. See it. See it. See it. Okay, well, I'll work on that. Anyway, finish this off real quick. I tested this out. I just assumed I didn't think a new light would be an issue. It's a better light. There you go. So know what n equals a here, right? So since this works for all n greater than equal to a, we want to show this for all n greater than equal to a, if n equals a, that means that p of a would imply p of a plus 1. And so what that means is, I'll rewrite like the logic chain thing right here. If we have true equals, or if we have that p of a is equivalent to true, and we know that p of a would imply p of a plus 1, that means that p of a plus 1 is also true. It connects to the truth, right? And then also, since this works for all n greater than equal to a, it also works for n equals a plus 1, right? When n equals a plus 1, we get p of a plus 1 implies p of a plus 2. So this also implies p of a plus 2 up here. And then so that's also going to imply p of a plus 3, and p of a plus 3 is going to imply p of a plus 4. Once you get bigger than equal to a, once you have one, it implies the next one. This is the whole domino effect thing. So this creates an infinite chain here, all connected back to the truth through the base case. So therefore, it's true for all these n. So the way this proof works is you'd say, so this is what we want to show, but actually show it what you do is you say let n be any arbitrary / particular integer such that n is greater than or equal to a. Now we're trying to prove a universal statement here, a universal conditional. So we're going to assume p of n and then show p of n plus 1 must logically follow. So assume p of n, show p of n plus 1 must logically follow. That proves this right here where we're trying to show. And so then we can finally have our conclusion. Therefore, for all n greater than or equal to a, p of n is true. Yeah, so here is the grand idea of how to prove something by weak mathematical induction right here. It's just a domino effect. Any questions on that? Good. We've already read that before. I just want to go over that again. So now let's talk about specific things about this, though. For example, we should need to be really careful here. Right, we want to show that for all n greater than or equal to a, for all n greater than or equal to a, I just saw that. Is that better? It's better. So I want to show that for all n greater than or equal to a, p of n implies p of n plus 1, right? But the point is we need to start at a. We don't want to start at a plus 1 or a plus 2, anything like that. So what I'm going to say here is we need an inductive step to overlap with base case at one point. So that point is a, right? The base case proves that p of a is true. And then we want the inductive step here to overlap with a. You want to show p of a implies p of a plus 1, p of a plus 1 implies p of a plus 2. The point is, though, the inductive step needs to be able to prove p of a implies p of a plus 1. So our in here wants to start at 1, be greater than or equal, start at a. So it'll be greater than or equal to a here. If we had a plus 1, there'd be a gap. So if we had our logic chain, we drew it again. If we have true equals p of a, but let's say this was not a, but this was a plus 1. This is a plus, this is n greater than or equal to a plus 1 here, well, then we'd be able to prove that for all n equal to a, p of n implies p of n plus 1. So that since n starts at a plus 1, we could prove that p of a plus 1 implies a plus 2. So we could have p of a plus 1 implies p of a plus 2. It says a plus 2 is bigger than this. We have p of a plus 2 implies p of a plus 3. On and on and on like that. But we have nothing connecting p of a to p of a plus 1. So this logic chain is meaningless because it never connects to the truth. It just says that if p of a plus 1 is true, then p of a plus 2 is true, then p of a plus 3 is true. But it's all contingent on p of a plus 1 being true, and nowhere did we prove that. We proved p of a is true, but we never connect that chain. So the point is we need to have this connection, which is why n has to start at a for that connection. Any questions there? Perfect. All right. So now the interesting thing about induction is that we normally do it on the integers. That is crazy. What's happening? Maybe you get a fluorescent light or something. So we normally do it on the integers, but we really don't have to. We could do it on really anything that you can list, right? Because the whole idea of induction is like if you can prove p of a, you can prove p of a plus 1, then p of a plus 2, p of a plus 3. It's like the domino effect. But really, it doesn't matter if all of these dominoes are integers. It just matters that we know how to get from one domino to the next domino, if that makes any sense. So what we really care about is that that our set's listable. So I'm going to write down. Can really use induction on any set that is listable. Oh, it's blurry again. It's blurry again. Thank you. Oh, it does not have to be natural algebra. So we could totally use induction on negative numbers, right? That's why everywhere in the like the thing we just went over, the form, we just said for all integers greater than or equal to a, but a could have been -5, for example. Could have been -100. Could have been anything. So you can really use induction on any set that is listable. But I'm going to say, i.e., a set that can be made into a sequence with integer indices. And here's what I mean by that. Let's try to prove the statement, the claim for all x in D, where D looks like this. Maybe it's -3, -2.5, -2, -1.5, -1, -0.5, 0, 0.5, on and on and on like that. Yeah. So this is D. I want you to know that for all x in D, p of x is true. Well, here's the thing, right? These definitely are integers, and they're definitely not positive integers at that either. But there's a nice pattern here. So this D can really be put into a nice sequence, right? Like if we call this a 0, or actually let's call it a 1. Let's call this a 1, I'll do it in green or pink. So let's call this A1, this A2, A3, A4, A5, A6, A7, A8, on and on, right? This is like we put in a nice sequence like this. And so the point is, proving this claim would be equivalent to proving for all n in the set of, or all n in the natural numbers, P of an is true. Let that sink in. Does that make sense? Like if we prove that, like proving that for everything in this set, -3, -2, -5, -2, that P of X is true, whatever this property is. Well, that means that for all n and n, P of an is true. It's because an, well, A1's this thing in D, A2 is this thing in D, A3 is this thing in D. So if we can prove the property is true for all of these an, we've proven it's true for everything in D. Because D really just is the set of all these ans. And then after that, the proof goes the exact same way. We'd say proof by induction on n. Yes, proof by induction on n. Then we'd have a base case. And that is let n equal to 1, because the first natural number is 1. So that n equal to 1. And then here we want to show that P of n, which is P of 1, is true. And then we have our inductive step. And here we want to show that for all n greater than or equal to 1, our inductive step overlaps our base case. P of n implies P of n plus 1. Here's how we do that. Let n be any integer such that P of n is such that, or sorry, let n be an integer such that n is greater than or equal to 1. Assume P of n. We want to show P of n plus 1 logically follows. So assume P of n, show P of n plus 1 logically follows. Then, I don't want to go in the glare section, so I'm going to say conclusion right here. Conclusion is that for all n and n, P of an is true. Thus, for all x and d, P of x is true. I'm going to fix this slide. I'm so sorry about this. I did not think this would be an issue. And by the way, I messed up here. I messed up here a lot. All of these places where I have a P of n, I really want a P of an, right? So I want to show that P of an here is equivalent to P of a1 is true. And here I want to show that P of an implies P of an plus 1. And so here I want to assume the P of an and then show P of a n plus 1 logically follows. Just because the property here, we're not working with integers, we're working with just whatever's in this sequence. But the sequence goes up by integers, right? Like we can identify everything in the sequence with an integer. Like the third thing is a3, which is -2. The fourth thing is a4, which is -1.5. So -2 and -1.5 aren't integers, but we can kind of list them. There's a first, second, third, fourth, fifth, sixth, seventh, eighth, ninth thing, 10th thing, on and on and on. Does that make sense? Yeah? The idea really is just use this idea of induction, of having the first thing prove the second thing prove the third thing prove the fourth, go up like that, the domino effect, except on a sequence rather than on just a set of integers. But it's really the same thing. Okay, well, if no questions, then we're gonna move it on. I don't even want to look at that crazy glare. So I'm keeping this paper up. So let's not talk about the real numbers then. So here's the question. Can we use induction to prove something about the real numbers? An example being maybe for all x in R, P of x. What do you guys think? Yes? No?
I say no.
Why say no, Safa?
I feel like it would be kind of hard to prove something that's irrational.
Irrational or rational?
Irrational.
Well, we could actually, so for example, if we wanted to prove that for all x in this set right here, I'll call it, it's going to start with pi, and then pi plus 1, and then pi plus 2, pi plus 3. This set right here, just an integer plus pi, right? We wanted to show something was true about all those, right? With induction. This is very doable, right? Because, I mean, this is just like the first thing. This is your second thing, your third thing, your fourth thing, on and on and on like that. And so, I mean, we can really kind of identify everything in this set with this. We can make it a sequence. We can identify everything in this set with, come back, camera. Wow, this new setup changes everything. There we go. We can identify everything in this set with kind of like, this is the first, second, third, fourth, fifth. We can kind of line it up with the natural numbers. And so I think we can use induction on this guy, right? If we could just prove P of A1 And if we could prove for all n greater than or equal to 1, P of AN implies P of AN plus 1, well, then we prove everything in this set, right?
Yeah, but what about proving something if it's like less than 0? Could you also like do that, or?
Yeah, we did that in the last example, right? Where we had our set was -3, -2.5, -2, -1.5, -1, on like that, right? So we said this was A1, this was A2, A3, A4, A5. It really doesn't matter what these numbers are in the set. It just matters how they connect to each other, right? So if we can make a proof where you can prove P of A1 is true, and you can prove that for all n greater than or equal to 1, P of AN implies P of AN plus 1. If you can prove the thing is true for your first set, for your first element, and then prove it being true for your first element, or then prove that you can get from one element to the next, you can prove P of AN implies P of AN plus 1. That's induction. There's your chain right there. It has nothing to do with the fact they're negative. It has to do everything with the fact just kind of how we can go through these things. If we can prove the first one, and then we can prove that you can get from one to the next, that's induction. It doesn't matter what we're doing it on. I hope that makes sense. Now let's talk about this guy right here. Same thing. These are all irrational numbers. Pi plus any integer is going to be irrational. We proved that with contradiction, actually. So pi plus 1 is irrational, pi plus 2 is irrational, pi plus 3 is irrational, the whole gamut. But we can still use induction to prove things about this. Because, that if we call this A1, this A2, this A3, this A4, right? We know how to get through everything in this set. So if we just prove for P of A1, then we can prove that once you have it for one, you can prove the next. If you can prove the property works for one of them, you can prove the property works for the next one. Well, there's your chain reaction. There's your induction. You start with this, that knocks down the next one, knocks down the next one, knocks down the next one, keeps going. So it really doesn't matter that the things in your set are irrational. Let's get back to the problem of the real numbers. Like, imagine you trying to write down the real numbers like this. And, you know, maybe even we'll just say about the positive real numbers to make it easier. Or I'll say real numbers greater than or equal to 0 to make it even easier. So, like, kind of like the first real number bigger than or equal to 0 is 0. What's the next one? Silence is fantastic here. Silence is the right answer. There is no next real number. Like, there are other real numbers after 0. There's 1, there's 0.5, there's pi, there's all these things. But the problem is, what's the next real number? Is it 0.1? Well, I would argue, what about 0.01? Or about 0.001? What about 0.00001? Right? The point is, there's no way to put the real numbers in a sequence. You can't sequence them out. Like, here's the first one, here's the second term, here's the third term, here's the fourth term. There's no way to do that, because what's the next real number? It makes no sense. There is no next real number. So we cannot use induction on R. The reason being, because the whole idea of induction is to use this inductive step. We go from like P of AN to P of AN plus 1. You go from one thing into the set to proving the next thing. It works for the next thing in the set. but what's the next thing in the real numbers? Doesn't make any sense. What do you mean by recurring numbers, Afra? Afra asked, what happens to recurring numbers?
It's like the value of pi that goes on and on and on. So that's the same. So the answer would be same.
Well, the pi goes on and on, but that's just one number. So,
for example, if we have 3.333, it goes on and on and on. So
are you saying, so induction, right? So all these proofs are like for all x and some d, you have p of x, where d is a set of numbers. But pi is just one number. It's not a set of numbers, it's just one number. So what I'm talking about here is that we can use induction on any set of numbers where you know how to get from one number to the next number. So it doesn't really matter to me that pi is infinitely many digits, or like 3.3333 is infinitely many digits. It doesn't matter to me. It just matters to me, do we know how to get from one number in the set to the next number in the set?
as in like finding the difference between the first term and the second term.
Oh, yes. So, no, I mean, exactly. That's the exact right point. If we're trying to prove this for the real numbers, right? It's kind of like, I mean, an excellent question is, what's the next number after pi? After 3.1415926, after that goes infinitely many digits, what's the next number? You know, you kind of want to increase like one of the decimal digits by one, but which one? It goes on infinitely forever. So so that's the reason why you can't use induction in the real numbers, is because you can have digits that go on forever, and so you can kind of get infinitely many. You can get infinitely precise, and so you can't just go up by the next one, because there is no gap between the real numbers. The gap gets smaller and smaller and smaller and smaller and smaller the more digits you take, and we take infinitely many digits. Is it making sense to you guys? Come on. Someone help me out. What are you guys thinking?
Yeah, it's clear to me.
Making sense? Yeah. So we can't use it on the real numbers. And we can't use it on anything like the real numbers like that. Here's the weird thing. The rational numbers. You would think that, like, what's the next rational number after 0.5? Makes no sense, right? Technically, you can order the rational numbers in a sequence so it works. We're going to do that later in the year. That's very, very interesting. It's one of like the coolest math things to prove. But don't worry about that. The point is, you can use induction or anything that you can put in a sequence, anything you can list, you can use induction on. But things that the real numbers that you can't list out, you can't use induction on. So I'll say things or sets you can't list, like R, you can't use induction on. Okay. So that's the end of week induction. That will be on your test tomorrow. So now let's do some more strong induction. Yeah. So let's do strong induction. Let's talk about that. So strong induction, we've done a couple of examples. But here's the idea on strong induction, very similar to regular induction. So to prove that for all n in a set of integers such that it's bigger than a, we have that P of n. To prove this using strong induction, it goes as follows. We have a proof, and we say proof by strong induction on n. And then we have a base case. And here's the weird thing about the base case in strong induction. You can have more than one base case, like more than one things that you verify at the start. We'll see why in a second. So for the base case, they'll say like let n equal to a, prove P of a, let n equal to a plus 1, prove P of a plus 1, all the way down to let n equals some b, and then you can prove P of b. So you're gonna have this many base cases from A to B. It could be 1, it could be 100. Then you have an inductive step. And now the inductive step goes like this. It says, so the inductive step, in this step, you want to show that for all n greater than or equal to b, we can use everything less than b to prove b, or to prove P of b plus 1. So that means we can use P of a plus 1, and P of b. If we know that everything's true up to b, then we can show that P of b plus 1 must be true. This is the idea. No, don't do this to your camera. This is the idea behind strong induction. Why? I don't understand. We go class without any issue. There we go. So we can do that right there. Or i.e. put a little more formally. i.e. we want to show that for all n greater than or equal to b, if P of k is true for all k such that 1 is less than, or such that a is less than or equal to k, less than or equal to, oh, I'm sorry. This is the first step. The first step is we want to show that everything up to b will prove P of b plus 1. But in general, we want to show that everything up to n will prove n plus 1. Sorry about that. So for all greater than or b, if P of k is true, for all cases that a is less than or equal to k, less than or equal to n, show P of n plus 1 must logically follow. And then our conclusion is that P of is that for all n greater than or equal to a, P of n is true. Yes, good. Sorry for the mistake, but yes, this is proof by strong induction. And the big difference is weak induction just uses P of n to prove P of n plus 1. But strong induction uses everything up to P of n to prove P of n plus 1. Starting at P of a, all the way to P of n. So what that looks like is if we have like our logic chain here thing, what that looks like is we have P of a, and that's true by the base case. P of a plus 1 is true by the base case, all the way out to P of b. All of these are true by the base case. And then, since b is bigger than or equal to b, right? If our inductive step is true, we can prove everything up to b to prove P of b plus 1. So that means we can use this, all of these together to prove P of B plus 1. And then since B plus 1 is greater than or equal to B, we can prove everything up to B plus 1 to prove it works for B plus 2. So that means we can use this all together with this to prove P of B plus 2. And then we can use this, all this together to prove P of B plus 3. So it's a bit messier. It's not quite as elegant as Still's weak induction, but it works, right? It's the exact same idea. Once you prove these base cases, and we can prove that for everything up to n, you can prove n plus 1, well, then this is the chain reaction that keeps feeding into itself. Once you have P of B plus 1, well, we already have all these by the base case. We have P of B plus 1, so we can prove P of B plus 2. And once you've proven P of B plus 2, well, we've already proven P of B plus 1 in all these, so we can use all these together to prove P of B plus 3. So it just feeds back into itself. It constantly keeps going up and up and up and proving everything in our set.
So it's like taking the sum of all the previous values to prove the next one?
Not the sum. Because remember, these things right here aren't numbers, they're statements. They could be saying that the statement could be for all n in this set right here, for all n in this set right here, we could have that sine of n is bigger than cosine of n, or something like that. It's a statement. But the idea is, if you can show that all of these statements in the base case are true, and you can show that all of the statements up to n being true will prove that the statement of n for n plus 1 is true, then you're good. So these things are statements. So we're not summing anything here. We're combining the statements together. We're saying that if you know P of A, and you know P of A plus 1, and you know P of A plus 2, and you know all the way out to P of n, then you also can prove P of n plus 1.
So it's like for my P of n plus 1 to be true, the previous statements have to be true.
Yeah, or really more the other way around, because that would be the converse. We want to go this way, saying that if these are true, then this will be true. But yeah. Well, that makes sense. I think it makes a lot more sense with an example. So let's just do an example. But this is the basic form. And and the thing to notice, remember, again, inductive step overlaps with the base case. Because our inductive step starts at greater than or equal to B, right? And our last base case is P of B. We always want that to be the case. We always want that overlap, because we don't have that overlap, then we don't have this first chain right here. We could prove that P of B plus 1 is we're missing this step. So we need the overlap. It's harder to see with this drawing because you can't just erase one chain. It's the same idea. All right. So kind of the art is figuring out how many base cases you need. So let's do an example. And the example goes like this. Yes. So first I'm going to define us a nice sequence. So define the sequence AN as follows. So we're going to have actually, let's call it HN just to be different. So you have H0 equals 1. H1 equals 2. And H2 equals 3. These are our initial conditions. And then we're going to recursively define this sequence. So we're going to have H of K equal to the 3 previous terms for all K greater than or equal to 3. So what that means is that we're trying to calculate H of 3. Well, that's just going to be the sum of the 3 previous terms. That's going to be H of 2 plus H of 1 plus H of 0, which is 3 plus 2 plus 1. And then H of 4 is going to be H of 3 plus H of 2 plus H of 1, the 3 previous terms, which is H of 3 found out 6, H of 2 is 3, H of 1 is 2, so it's going to be 3 plus 6 plus 2, which is going to be 11. On and on like that. So here's the claim about this sequence. The claim is that for all n greater than or equal to 0, so for all integer n greater than or equal to 0, h, the nth term of the sequence is less than 3 to the n. Less than or equal to 3 to the n. That's the claim. And we can see it kind of makes sense, right? Like h of 0 equals 1, which is less than or equal to 3 to the 0, which equals 1. H of 1 equals 2, which is less than or equal 3 to the 1, which equals 3. H of 2 equals 3, which is less than or equal to 3 squared, which equals 9. I'm sorry, yeah. H of 3 equals 6, right? Which is less than or equal to 3 cubed, which equals 27. H of 4 is 11, less than or equal to 3 to the 4th, which equals 81. So this seems to make sense. For all the values we're checking, we're getting that h to the n truly is less than 3 to the n. So this right here, we'll call this our P of n. P of n is true if h of n is less than or equal to 3 to the n. So I think the best way to actually prove this is true is with strong induction. The reason being, we can't really use a direct proof on this. I wish we could, but the issue is we don't really know what hn is. For any n, we kind of have no idea what hn is. We only know what it is relative to its previous values. So it's hard to say, like, let n, it's hard to say, let n be any arbitrary element of natural numbers, consider h of n or something like that, because, well, h of n is meaningless at the previous values. But this is exactly why induction makes so much sense, because induction is the way to prove the next value from the previous values. So it makes total sense that induction might be the key here. So I'm going to say proof by strong induction. Proof by strong induction on n. Now we're going to come back to the base case. The reason being that we kind of have to see how our inductive step works first. We kind of need to know, what does our inductive step need before we need to know how many initial conditions we need. You'll see that in a second. So if we look at our inductive step, we want to show that for all n greater than or equal to some b, whatever it is. Well, we know in the base case, we know we're going to start at 0. So we're going to have to at least have that. So we could say let n equals 0. Note that h of n equals h of 0, which equals 1. By definition, 1 is less than or equal to 3 to the 0. We know we're going to need to start with that base case at least. We might have more in between. Let's see what the inductive step means. So the inductive step is going to say for all greater than or equal to some b, we're going to fill that in a second. P of 0 all the way up to P of B, or sorry, P of N, can be used to prove P of N plus 1. That's the idea, right? So this is what we want to show. I.e., we want to show is that for all n greater than or equal to b, if P of k is true for all k between 1 or between 0 and n, then P of n plus 1 is true. That's what we're trying to show. And let's look at the idea here. Let's see if this makes any sense to us at all. So the idea here would be, let's say we knew the claim was true for everything up to n. So let's say we know that what's P of 0? We know P of 0 is h of 0 is less than or equal to 3 to the 0. We know h of 1 is less than or equal to 3 to the 1, all the way up to h of n is less than or equal to 3 to the n. Now we really want to show that h of n plus 1 is less than or equal to 3 n plus 1. Oh, you guys can see that. Let me get the old whiteboard out so we can do our SI. So we really want to show that if we know h of 0 is less, don't do this to be careful. I'm sorry for technical difficulties, everybody. Yeah, so we're showing that h of 0 less than 3 to the 0, h of 1 less than 3 to the 1, all the way out to h n less than 3 to the n. We really want to show that we can combine all this together to prove that h of n plus 1 is less than or equal to 3n plus 1. And let's just kind of go about it. So we know by definition, right, that h of n plus 1, if we look at our recursive formula, that's going to be the sum of the 3 previous terms. So h of n plus h of n minus 1 plus h of n minus 2, right? That's what we want. But by this right here, we know that everything up to n is such that h of n is less than or equal to 3 to the n. So that means that h of n is less than or equal to 3 to the n. H of n minus 1 is less than or equal to 3 to the n minus 1. And h of n minus 2 is less than 3 to the n minus 2. Right? We're assuming that the claim holds for everything up to n. We want to show it holds for n plus 1. So if it holds for everything up to n, then it holds for n minus 1, and n minus 2. So h of n is less than 3 to the n, h of n minus 1 is less than 3 n minus 1, h of n minus 2 is less than 3 n minus 2. All right. But notice that 3 to the n minus 1 is certainly less than 3 to the n, right? It's 1 power less. And 3 to the n minus 2 is certainly less than 3 to the n as well, right? Because it's 2 powers less. We had to multiply this by 3 2 more times to get to 3 to the n. So clearly 3 to the n minus 2 is less. So this is less than 3 to the n plus 3 to the n plus 3 to the n, which equals 3. But it's 3 copies of 3 to the n. But 3 times 3 to the n, what's that? That's 3 to the 1 times 3 to the n, which by our exponent rules is 3 to the n plus 1. So the point is, this is the inductive step right here. This is the place where we show that if everything up to n follows the claim, hn less than 3n, hk less than 3k, then hn plus 1 will be less than 3 to the n plus 1. Just because each of these will be less than 3 to the n, and so if you add them together, it's clearly going to be less than 3 to the n plus 1. Now here's the question though. I used this recursive formula. This recursive formula doesn't work everywhere, right? When does this start working? For what indices does this work?
One is greater than or equal to 2.
Yeah. Yeah. The index has to be bigger than or equal to 3 to use the recursive formula. So we want n plus 1 to be greater than or equal to 3, meaning we need n to be greater than or equal to 2. Yeah. So that's going to be our b here. We're going to want n to be bigger than or equal to 2. Gosh, these markers are running out too. Well, n to be bigger than or equal to 2. And so then in the base case, we want to fill everything in. We're going to want to prove it for n equals 1, and we're going to prove it for n equals 2. But we'll do the rest of that proof next time. For now, it's been a good day. I hope everything's making sense. I hope induction's clicking. The whole, move to the next one, move to the next one, move to the next one. We'll finish up strong induction next time, and then move on. Move on to our topics section. Any questions, anybody? Today felt very technical. I feel like we did have a lot of fun today. But I mean, technical can be fun, I guess, right? I mean, like you always see, like in figure skating or gymnastics or like snowboarding or whatever. People always talk about like, oh my gosh, like she's such a technical skater. Like that's such a hard technical move, or snowboard or whatever it is. And I have fun watching snowboarding. Ice skating less, I'll be honest. I like it when they put their arms in and they go really fast. That's about it. I'm done, by the way. If it wasn't clear. Anyone have any questions?
Are there more examples of this? Like I know you sent an email about examples, and I haven't had time to read any of that. But like, are there more strong induction examples that we could work through and then maybe bug you with later?
Yes. So if you have the textbook and you go to section 5.4, then there's a bunch of examples you could do. You totally bug me about them. This is actually one of them right here. But I also did a link to a Fibonacci example that I did. I worked out totally, and that's in last Thursdays. If you go to that page in Canvas, at the very bottom says like extra examples optional. There's Fibonacci one right there.
Right.
Or you could just Google strong induction examples. So right now we have a few. We have the Fibonacci. We have the fundamental theorem of algebra example. Then we have the other weird example about where I made a sequence where the index was the opposite parity to what the sequence actually was. Then we have the one from the homework, where it's kind of like the opposite of that, but similar. We have this one right here, and then we have the Fibonacci one. So There's kind of 5 examples out right now. This one even worked through entirely. We'll finish it, but it's not going to be on the test. Yeah, I took strong induction off the test because there was issues with the link on Thursday, and also we just covered it. Let's just do it later. I want to get it done so we have a nice demarcation between this section and the next section, but test 3 is going to have strong induction on it, and everything else is going to be not even very proof related. There's going to be proofs, but proofs are more a tool. Like this whole time we've been doing proofs for the sake of proofs. They're just like, here's a new cool proof technique. Here's a new proof technique. That's fun. Now we're going to start moving on to actually using proofs as a tool to prove things about other things we care about, which is interesting. I mean, it's kind of like it's kind of like a chicken and the egg. It's like, what came first, the problem or the proof? Or what's more interesting? I don't know. They're both kind of fun because, like, knowing the answer to the problem leads you to more proofs. So it works out. Anyway, any more questions? Good question, Herman. All right, and I'll see you next time with one more proof class, and then we can start to get weird. Then we can start to get I think it's fun. Don't get me wrong, I love these proofs. I think they're fun, but I think they're getting kind of stale. We're starting to get some new stuff. But anyway, have a good day, everyone. See you later. Good luck on the test. If you want to come to the review session, it's going to be tonight at 7. I'll make an announcement about that right now.
Great, thank you.
You're welcome.
Peace out, Professor.